This video is about oxidation states. Many reactions involve the transfer of electrons from one species to another. We use oxidation states to keep track of electron transfers. The systematic naming of compounds also makes use of oxidation states. The oxidation state or oxidation number, those words are interchangeable, of an element in a simple binary ionic compound is the number of electrons gained or lost by an atom of that element when it forms a compound. In the case of a single atom ion, it corresponds to the actual charge on the ion. In molecular compounds, oxidation states do not have the same significance they have in binary ionic compounds. Oxidation states, however, are very useful. They're aids in writing the formulas and in balancing equations. In molecular species, the oxidation states are assigned according to an arbitrary set of rules. The most electronegative element, which is the one that's further to the right and higher up in the periodic table, is assigned a negative oxidation state, and the element further to the left and lower down in the periodic table is assigned a positive oxidation state. Some rules for assigning oxidation states are going to be shown here. These rules are not comprehensive, but they cover most cases. In applying these rules, keep in mind two important points. First, oxidation states are always assigned on a per atom basis. Second, treat the rules in order of decreasing importance. The first rule that applies takes precedent over any subsequent rules that seem to apply. The first rule for assigning oxidation states is that the oxidation state of the atoms in any free uncombined element is zero. This includes polyatomic elements such as hydrogen, oxygen, phosphorus, and sulfur. The oxidation state for each one of these elements is going to be zero. It does not matter how many of those elements there are. So for example, phosphorus, the formula is P4. The oxidation state for the phosphorus for all of those elements in that phosphorus molecule is going to be zero. The second rule is that the oxidation state of an element in a simple monatomic ion, meaning one atom, is equal to the charge on the ion. So whatever the charge is on that ion, that's going to be equal to the oxidation state. So for example, the chloride ion would have an oxidation state of -1. Rule 3. The sum of the oxidation states of all atoms in a neutral compound is 0. Rule 4. In a polyatomic ion, the sum of the oxidation states of the constituent atoms is equal to the charge on the ion. So just like 3, being that the sum of the oxidation states of each of the individual atoms has to equal 0 for a neutral compound, if you have a polyatomic ion, the sum of the individual oxidation states of the atoms has to equal the charge of the polyatomic ion. Rule 5 is that fluorine, since being the most electronegative element, has an oxidation state of -1 or -1 in all of its compounds. Rule 6 is that hydrogen has an oxidation state of +1 in compounds unless it is combined with metals, in which case it has an oxidation state of -1. Examples of these exceptions are sodium hydride and calcium hydride. Oxygen, which is the second most electronegative element, usually has an oxidation state of -2 in its compounds. There are just a few exceptions to this rule though. The first exception is that oxygen has an oxidation state of -1 in hydrogen peroxide, H2O2, and in peroxides, which contain the O2 2- ion. Examples of this would be calcium peroxide and sodium peroxide. Oxygen has an oxidation state of -1/2 in superoxides, which contains the O2 -1 or 1- ion. Examples are potassium superoxide and rubidium superoxide. When combined with the more electronegative fluorine in OF2, oxygen has an oxidation state of +2. The position of the element in the periodic table helps to assign its oxidation state. So group 1A elements have oxidation states of +1 in all of their compounds. Group 2A elements have oxidation states of +2 in all of its compounds. Group 3A elements have oxidation states of +3 in all of their compounds, and there are a few exceptions to that. Group 5A elements have oxidation numbers of -3 in binary compounds with metals, with hydrogen, or with the ammonium ion. Exceptions are compounds with a group 5A element combined with an element to its right in the periodic table. In this case, their oxidation states can be found by using rules 3 or 4. Group 6A elements below oxygen have oxidation state numbers of -2 in binary compounds, with metals, with hydrogen, or with the ammonium ion. When these elements are combined with oxygen or with a lighter halogen, their oxidation states can be found by using rules 3 or 4. And finally, group 7A elements, which are the halogens, have oxidation states of -1 in binary compounds with metals, with hydrogen, with the ammonium ion, or with heavier halogens. When these elements, except fluorine, so chlorine, bromine, iodine, are combined with oxygen or with a lighter halogen, their oxidation numbers can be found by using rules 3 and 4. These are the 8 rules to determine the oxidation states for any element that you might come across. Now let's work some examples. N2O4. What is the oxidation state of the nitrogen in N2O4? So we first assign the oxidation states to elements that exhibit a single common oxidation number. And we recall that the oxidation states are represented per atom. The sum of the oxidation states in neutral compounds is 0, and if it was an ion, it would equal to whatever the charge is on this ion. So in this case, this is a neutral compound, so that means the sum is going to be equal to 0. Oxygen has an oxidation state of -2. This is not one of the exceptions to this, so we can write -2 above the oxygen. Since we have 4 oxygen atoms, the total oxidation state will end up being -8. And so since the sum of the oxidation states have to equal 0, that means the total oxidation state for the nitrogen has to be a +8. Since we have 2 nitrogen atoms, one of the nitrogen atoms will have an oxidation state of +4. So in this molecule, N2O4, dinitrogen tetraoxide, the oxidation state for the nitrogen will be a +4. Now what about ammonia? NH3. Again, the sum of the individual oxidation states has to equal 0. This is a neutral compound. Hydrogen has an oxidation state of +1. It's not bonded to a metal. So hydrogen's oxidation state will be a +1. We have 3 hydrogens. That gives us a total of +3. This has to equal 0. So that means the nitrogen has to be a -3. So in ammonia, the nitrogen has an oxidation state of -3. And in N2O4, the nitrogen has an oxidation state of +4. What about the compound HNO3? Again, the sum of the oxidation states has to be 0. Oxygen is going to be -2. It is not an exception. We have 3 oxygens, so the total will end up being -6. The oxidation state for the hydrogen will be a +1. Since the sum has to equal 0, 1 plus some value -6 equals 0. That means this has to be a +5. So the nitrogen has an oxidation state of +5. What about the polyatomic ion nitrate, NO3 minus 1? Now this is a polyatomic ion. It is not a neutral compound. That means the sum of the oxidation states has to equal whatever the charge is on a polyatomic ion. In this case, it is -1. Oxygen is going to be -2. We have 3 of those, so the total charge is going to be -6. And the sum has to be -1, which means nitrogen is going to be a +5. And then one last one. What about the molecule nitrogen? Molecule nitrogen, this is a element in its free element state, so therefore the oxidation state for this is going to be 0. So nitrogen can have an oxidation state of +4. It can have an oxidation state of -3, +5. This one would also be a +5 or a 0 depending on what type of compound it is.